So we're continuing on with factoring. Now there's 4 different types that we're going to look at today, which I consider special factors. They have kind of special properties to them. But for the first one, it's not going to really change too much. And we're going to cover 2 of the 4 today, and then we'll cover the other 2 tomorrow. We could have probably gotten through all 4 of them, gotten this all done in one day, but I'm just going to put it across 2. Now the first type that we're going to look at is these here. Now, they do have a special name. These are called perfect square trinomials, and they're going to have a special property to them. And there is a method that we could go through using a set formula to make it easier to solve it. Well, quote unquote, easier to solve it. But I don't think it's any easier than just using the ways that we've been doing the last 2 days. So when we look at this here again, we're going to check to see if there's a greatest common factor. And well, between 4x squared, 4x, and 1, there's not. So we'll use our 2 sets of brackets with, or parentheses with 3 spaces. So we're just going to stick with this here. Now, because the 1 is positive, the signs are the same, and they match the sign of the middle term. So it'll be negative and negative. So really nothing's changed from what we did yesterday or Tuesday. Now we need to find the factors of the first and third term. Now we normally look at 4x squared, the first term, and find its factors, but, well, the third term is 1. What's the factors of 1? 1 and 1. If there's an easy set of factors, I go for it first because one less thing to do. Now we can look at the factors of 4x squared. Well, we know the factors of x squared are going to be x and x. And the factors of 4 are 1 and 4 and 2 and 2. So we do have 2 different options to look at here. So what do we want to try first? 1 and 4 or 2 and 2? Let's try 2 and 2. So we'll have 2x and 2x. Now when we check this here, 2x times negative 1 will be negative 2x. Negative 1 times 2x will be negative 2x, which will give us negative 4x. So this is the correct set of factors. So this here is our answer. Now again, you're probably looking at this and saying, okay, why is this really considered a special set of factors? Well, if we look at the factors, what are they? We have 2x minus 1 and 2x minus 1. So really, this here, we could actually write it as 2x minus 1 squared. This is why they call it a perfect square trinomial. And there is a set formula for if we have this ax squared plus, it's really a bx plus b squared, and there's a way that we can actually go about using a and b to figure this out. But it takes more time to figure out how a and b work together in the squares. We could have just done our normal steps. There's no real advantage to using the set formula for these here when we can just use our normal steps to solve it and to find the factors. And that's what we're going to look at these here. We're going to look at a few of these really. We can look at 2 of these perfect square trinomials, and then we'll kind of move on. And the next one's actually going to be easier. I think you'll like the next one better. And we look at this here, 16b squared, negative 40b, and 25. There's not a greatest common factor. There's not a number or variable that will go into all 3. So we have our 2 sets of parentheses with 3 spaces. Here's what we do first. The next step is to figure out the signs. Since it's positive, the signs are the same, and they're both negative. And now we need to find the factors of 16b squared and 25. Well, the one we know for sure is that we're going to have b and b. And that's the only way we can get b squared for this problem here. Now we're looking at the factors of 16, which is 1 times 16, 2 times 8, and 4 times 4. Well, 25 is going to be 1 times 25 and 5 times 5. So we have multiple sets of factors that we can look at here. So for 16, do we want to try 1 and 16, 2 and 8, or 4 and 4 first? What do you think we want to try first?
Let's go 4.
Let's go 4 and 4. So that works for 16, and then for 25, we can have 1 and 25 or 5 and 5. 5 and 5. And lastly, we can check this here. Well, 4b times negative 5 will be negative 20b. Negative 5 times 4b will be negative 20b, which gives us negative 40b. And this works. Now, it's a little bit helpful because, again, these are special factors, so it's going to work out this way. But again, we always need to check and make sure that this works out. So we can write this, our answer as 4b minus 5 times 4b minus 5. And 4b minus 5 squared. This is also the same answer. These are the same thing.
So on the test, if we circle the top one, do we get the same amount of points if we simplified it?
Yeah. Because both of these are in simplest form. Any questions on this here? So this here isn't really any different than what we did yesterday. It's just, it works out uniquely, or kind of works out nicely, that both factors are the exact same thing. That's the only real difference between the two. So I'm not going to worry too much with this one here. Now this next one here, n squared minus 25, this one is special. And we call this one here the difference of perfect squares. Mainly because n squared is a perfect square. It's n times n. 25 is a perfect square. It's what? 5 times 5. And we call it a difference because they are subtracting. Difference is subtraction. So we have the difference of perfect squares. We have two perfect squares being subtracted. Now we had a theorem which states that a squared minus b squared is equal to a minus b times a plus b. And this is one of the few formulas, or kind of with factoring, besides kind of this one here and sum and difference of perfect cubes, that actually makes factoring a little bit faster. Because if I can recognize that n squared and 25 are both perfect squares, I can kind of jump straight through to this here. Now, kind of as a way to see this, well, n squared is already set up as a perfect square, or something squared. 25, I can rewrite this as 5 squared. Just kind of see, so we can see a and b. Because a in our case is n, and b in this case is 5. So really, I can use this formula, and we would rewrite this as n minus 5 times n plus 5. That's it. Because as soon as we can see that it's a difference of perfect squares, we kind of simplify it down. We see what times itself is each one of the numbers. So we have n and 5. So it becomes n minus 5 times n plus 5. And that's it. This one here is, I feel like, is probably one of the nicer ones that we factor. Because once you start seeing this pattern, these go a lot faster than most other factors. So any questions on this here? Let's look at this one here. 16n squared minus 9. So we do have subtraction, so there's a good chance that we do have a difference of perfect squares. Well, 16n squared, a perfect square. Is it something times itself? Can we rewrite it as something times itself? Yeah, 4n squared. How about 9? Well, yes. 9 would be what? 3 times 3. So I can really rewrite this as 4n squared minus 3 squared. Yes? because we can rewrite it as 2 squares. And by our formula, that a squared minus b squared is equal to a minus b times a plus b, we can rewrite this as 4n minus 3 times 4n plus 3. So it's just really using this formula. And we get this here. Questions on this here? So really, for any values of a and b, any terms for a and b, we can use this difference of perfect squares, no matter what it is. Are we ready for the next one? Yes. I think we're good with this one here. Let's look at this one. I like this one better. Is this here a difference of perfect squares? It is, because 9 is a little bit easier to see, because 9 is just, well, you'll flip it right, 3 squared. Because that one's a little bit easier to see. We can do that. You've been doing that for quite a while now, seeing that 9 is the same as 3 squared. But can I write a to the 4th as something squared? A squared, because a squared squared is the same as a to the 4th. Because powers of powers multiply. So we can do that with any higher power. Could we do it with 6? A to the 6th? Because it would be what? Because we could say a to the 3rd, because powers of powers multiply. So really, any even power, we can use the difference of perfect squares with it. So again, we said a squared minus b squared is equal to a minus b times a plus b. So this here would be what? A squared minus 3 times a squared plus 3. And that's it. Questions on this here? So are we good with this one here? Yes? I mean, it's a little bit different because we had to think a little bit more outside of the box with the fact that we had to rewrite a to the 4th as a squared squared. But otherwise, it works the exact same. So this one here, we're going to do the similar thing, yes? Because we can say that k squared squared minus 6 squared to get this a squared minus b squared, where our a term is k squared and our b term is 6. Now this here would give us k squared minus 6 and k squared plus 6. Any questions on this here? Any questions on any of this here so far? Okay. X to the 4th minus 81. I'm going to give you a few seconds here. I want to see if you can get this one here. See if y'all can factor this one completely. Yeah. So when we look at this here, I believe everybody at least got to this here, yes? We're able to see this. So you're getting 2. Now you're kind of wondering, where am I getting 3 from? Well, when I look at this here, so again, difference of perfect squares is 2 things that are perfect squares being subtracted, yes? Because here, Our first one, x squared minus 9. X squared and 9 are both perfect squares. Yes? So I could rewrite this first one as x minus 3 and x plus 3. So we could factor that one down again because it's a difference of perfect squares. There's no such thing as a sum of perfect squares. So this here is just going to be x squared plus 9. So x squared plus 9 doesn't factor because if we were to try to factor it or solve it, it would be complex solutions. It would be complex factors. So we don't factor it. Well, if you're wondering about the previous ones, well, if we look at this one here, well, 6, is it a perfect square? No. There's not a number multiplied by itself that's 6. And the one before that is 3. 3 is not a perfect square. So these here are factored completely. It just worked out that with 81, well, we got x squared minus 9. 9 is still a perfect square, so we had to simplify it again. And this is where we're going to stop, is with this one here. Because this here is not a difference of perfect squares. This is actually coming on to our sum and difference of perfect cubes. And we've covered this once before because we talked about remembering how to find the signs with the dating story, which we only used once. But we'll cover that in